This conference will now be recorded.
Hi, this is Math 211, Section 2.4 video. We're just going over a few of the extra examples that we didn't get to in class. I skipped over this one because it's an application of this limit that we said you kind of just need to be familiar with, which is that sine of x over x as x approaches 0 is equal to 1. There will be a proof of that one. I'm going to put that up later, but just mainly right now we're just seeing if you can use this. And it works if the inside here matches the denominator. So the problem is these don't match. But one thing we can do with limits is we can pull out a coefficient. So if we pull out a 1/3, we get limit as x approaches 0 of sine of 5x over just x. Now that still doesn't fix anything. So there is another trick that you can do, because this is kind of, and this is kind of a sleight of hand. If we have something and we need to alter it, we can multiply by a 5 and put this back inside, but we have to make sure we do 5 over 5 because that's really like multiplying by 1. So I'm multiplying by 5 over 5, which is a 1, because I need the 5 in the denominator down here. So just like we can pull a coefficient out, we can put 1 back in. But the 5 on top is going to stay outside with the 1/3. So it becomes 5/3, the limit as x approaches 0, over sine of 5x over 5x. Now that this matches, and this is just like having this limit up here because those are identical, we see that we can evaluate this limit now that we know that definition of that limit as 1. So this is 5/3 times 1, which is just 5/3. Okay, now for example 3, we wanted to do this one two different ways. We wanted to do the quotient rule first, then we want to rewrite everything in terms of sine and cosine, and then find the derivative that way and see which one is better. So when we look at the very first part, if we're going to do this by the quotient rule, we need to list out what is our top, which is tan x minus 1. Top's derivative would be secant squared x, and the 0 for the minus 1, so there's nothing there. The bottom is secant x. The bottom's derivative then would be secant x tan x. So now if we use our formula, y prime would be the bottom times the derivative of the top minus the top. That's not supposed to say tax. It's supposed to say tan x times the derivative of the bottom, tan x, all over the bottom squared. So we would then work some of this out. So that's going to be secant cubed x minus, now we'll need to distribute here, so that's going to be secant x tan squared x. This is minus times minus, and then it's times this, so it's going to be positive secant x tan x all over secant squared x. Now what we'll note right away is that we see that there is a secant on everything on top, so we can pull that out. And that leaves me with secant squared x minus tan squared x plus tan x all over secant squared x. And we can reduce this, so that would be secant squared x minus tan squared x plus tan x over secant x. This looks oddly like a Pythagorean identity. Remember, our base formula for that is sine squared plus cosine squared equals 1. And if we divide everything by cosine squared, notice that gives us a secant squared on this side. Oops, sorry. So that would be tan squared x plus 1 equals secant squared x. So notice, remember, if you subtract over the tan squared, you get secant squared minus tan squared x. So that means this whole thing can be replaced with a 1. So now I have that y prime is 1 plus tan x over secant x. So there's my derivative. Okay, the other way said, what if we changed all of these to sines and cosines, and then we did the derivative again using that? So let's start off again by just looking at our original function, and we're going to change everything to terms of sines and cosines. And I'll do this in a different color so you can see this. So this would be sine of x over cosine x minus 1 over cosine x. I would then simplify some of this if I could. So this is going to get a common denominator. So this is going to be sine x minus cosine x over cosine x, all over 1 over cosine x. So I haven't even taken a derivative yet. Then I would flip that and multiply by the reciprocal of the bottom. So that's times now cosine x over 1. The cosine x's are going to cancel out. So just my function is sine x minus cosine x. So if I take the derivative of that, that is going to be cosine x minus a negative sine x. So that's going to be plus sine x. Now the thing is, you have to show that those are the same thing as each other. So if we broke this guy up, this would be 1 over secant x plus tan x over secant x. That is that one's cosine. That's a pretty easy one. This one, you would need to write it as sine x over cosine x over 1 over cosine x, and you'll flip it and you'll just get the sine x. So this does equal that. So these are both different ways to approach this derivative. In the first case, we went straight to the derivative. We just essentially attacked it. And then that meant we had more nasty stuff to clean up in the actual derivative. When we did the conversion, when we turned it into sines and cosines, we were able to actually manipulate the equation a little bit before we started, and then the derivative was pretty simple to take. So that's just something to think about. And then this is our last example from this section. We are wanting to suppose that f of pi over 3 is 4 and f prime of pi over 3 is negative 2. And then they gave us some combination functions. G of x is f of x times sine x, and then h of x is going to be cosine x over f of x. So let's work with the g first. So we want to take g prime of x. Now notice this is a first function and a second function because f of x is different. We don't know what it is, but it's different than sine x. It's its own function. So we're doing a product rule to do that derivative. So g prime of x would be the first times the derivative of the second, which would be sine x. So that derivative is going to be cosine x, plus the second, which is sine x, times the derivative of the first, which we would just write as f prime of x since we don't know what it is. Now we know how to evaluate this because this would be g prime of pi over 3 is f of pi over 3 cosine of pi over 3 plus sine of pi over 3 times f prime of pi over 3. So we just have to know how to evaluate. These two are given. We just need to know how to evaluate sine and cosine of pi over 3, which remember is 60 degrees. So f of pi over 3 we know is 4. Cosine of pi over 3 is going to be 1/2. Sine of pi over 3 is square root of 3 over 2. And f prime of pi over 3 is negative 2. So this ends up being 2 minus a square root of 3 when we work out the individual pieces. So now for the next one, we're doing h prime of pi over 3. So this guy is a combination function as well. And we are looking at, this is what we're taking the derivative of. So I might write this one out a little bit more. So top is cosine x. Top prime would then be negative sine x. The bottom is f of x. So bottom prime is going to be f prime of x. So then when we write h prime of x, we would say it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, let's plug in what we know. This would be f of pi over 3. I'm actually going to pull the negative out to the front. That'll make it easier to do the calculations. Then sine of pi over 3 minus cosine of pi over 3, f prime of pi over 3, all over f of pi over 3 squared. Okay, so we're going to plug in what we know from up here. So that's a -4 now, and sine of pi over 3, we just worked out a minute ago, is square root of 3 over 2, minus cosine of pi over 3 was 1/2. F prime of pi over 3 is -2. And f pi of over 3 is 4, so this is 4 squared. So this will be -2 on the square root of 3 plus 1 all over 16. Now you could rewrite that if you want as 1 minus 2 square root of 3 over 16. Honestly, either way is okay with me. And that is it. So that finishes those notes.